Despite the fact that my last post may have made it seem that our chances of finding life are pretty minute, people are still looking. And no, I don't mean the people who are convinced that aliens have already visited us, although if they found some actual evidence, it would be pretty cool. Organisations like NASA, government agencies and private companies have all had a stab at looking for life. Before we can find life, we have to find places for life to exist. So this is where telescope-based astronomy comes into play. Of the thousands of exoplanets that we have unearthed, most of them were discovered by the Kepler Space Telescope. The spacecraft has a heliocentric orbit, which means rather than orbiting the Earth, it follows the Earth in its orbit around the Sun. It spent its 9-year mission gazing at the same patch of stars, which occupies roughly the same amount of space as your fist held against the night sky at arm's length. Kepler worked by looking for transits, the slight dip in a star's brightness when a planet passes in front of it. This tiny dip can actually tell us rather a lot about the planet. For example, we can figure out its size by how much light it blocks out when it passes in front, because for a planet at the same distance, a bigger planet will block out more light than a smaller planet. And we can also figure out how far away it is from its star by the length of the transit, which translates into the length of its orbit. Occasionally, we can also figure out what's in the planet's atmosphere. This is done using spectroscopy, splitting the light that travelled through the planet's atmosphere and looking for characteristic absorption spectra, black lines where the elements in its atmosphere have absorbed particular wavelengths. We can tell what's there by what's missing. So transits can tell us the volume of the planet, the distance from its star, and possible composition, but discerning the mass is usually impossible just using the transit method. But sometimes we stumble across multi-planetary systems like our own. If these planets are packed close together, then their gravity causes them to interact, meaning that their orbital period varies. This gravitational influence depends on mass, which means we can then figure out what their mass is. But usually we have to rely on other methods, like radial velocity, also known as the wobble method. Newton's third law says that for every action, there is an equal and opposite reaction. So when a star's gravity pulls on a planet to keep it in orbit, the planet pulls back. This causes the star to wobble back and forth. The effect is tiny, but we can detect it by measuring the changes in wavelength as the star moves towards or away from Earth. This is known as the Doppler Effect. When the star is moving away from the Earth, its light that it emits is redshifted, but when it moves towards the Earth, the light looks more blue. It's also the effect that means ambulance sirens sound different when they're coming towards you versus going away from you. And a benefit of this method is that it's easier to detect the mass, which means it's good in partnership with the transit method to give us a complete view of the planet. There are other imaging methods, although these are more rare, but they are still used, include direct imaging and microlensing. So direct imaging involves blocking out the starlight and just looking for the light that the planet reflects. This only works if the planet is far enough away from its star that we can discern the light that the planet reflects from the light that's emitted from the star. And the system also has to be close enough to us that we can detect the light, because the reflected light really isn't that bright. But from this, if we manage it, we can find out the orbit, the atmosphere, and it just feels more real as we can actually see the planet rather than infer it. Microlensing uses consequences of gravitational lensing predicted by Einstein, and is when light bends around a large gravitational mass. And we can look for this by looking for blips in high intensity as focused light appears brighter. However, these systems have to be in line with the bright galactic centre for us to be able to detect the background image being brightened, and this is relatively few stars compared to all the stars in the night sky, which makes it more difficult to find them. However, Kepler's success has meant that by far the most exoplanets have been found by the transit method. Unfortunately, Kepler is no longer in service, but has been replaced by TESS, the Transiting Exoplanet Survey Satellite, which launched on a Falcon 9 last year. Compared to Kepler, it's an accelerated mission, covering more stars in just 2 years by looking at brighter stars, which are easier to track. TESS's main role is to identify exoplanet candidates, but it's up to space telescopes like Spitzer, which observes mainly in the infrared area of the spectrum, and Hubble, which observes a wide range of wavelengths, as well as Earth-based observatories to confirm this exoplanet and find out more about what it's like there. Its distance from its star can tell us its possible temperature and what elements could exist in what state on its surface and its atmosphere, but spectroscopy is what can tell us what actually is in its atmosphere. For example, biomarkers. These are indicators of life, and a common one is oxygen, as oxygen, if it's not replenished by processes like photosynthesis, oxygen just combines with other elements on its surface to form compounds. So if we found pure oxygen in its atmosphere, that would indicate that a process like life exists there, although it won't confirm life. If we want to find proof of life on exoplanets, we're gonna have to visit one. Sadly, we don't have access to warp drives or hyperspeed, so for now, crewed extrasolar missions and active exploration of exoplanets is pretty far away. In the near future, however, it's not so unthinkable that we could send uncrewed spacecraft to reach our first exoplanet in a relatively short amount of time. The initiative that I think is closest to feasible is Breakthrough Starshot, which is the brainchild of Russian billionaire Yuri Milner and the late Stephen Hawking. The project involves sending about 1,000 nanocrafts at 20% the speed of light to our closest star, Proxima Centauri, reaching its target in just 20 years, with the goal of flying by exoplanet Proxima b and beaming back images and data. It will be able to reach such high speeds as each craft is incredibly light, and as a system they'll be propelled by Earth-based lasers which have incredibly high power and high precision. By doing this, we'll be able to access astounding new science within a human lifetime of them being launched. Despite its potential, there are quite a few issues with the project. The main one being that the lasers require a lot of energy in order to reach their combined target output of 100 gigawatts. To put that into some context, you would need 40,000 wind turbines, which is 4 times the number in the whole of the UK, in order to power the array of lasers. A, that would be really expensive, and B, is it worth the resources, especially as it would be incredibly unlikely for this to be powered by totally carbon zero sources. As well as the insane energy requirements, there is a whole host of engineering problems that need to be overcome. And you can see this list on their website, which I'll link down below. Until we get past these difficulties, our search for ET is basically bound to our solar system, or passively exploring these exoplanets from afar using bigger telescopes. But when we do venture out into the galaxy or spot a strange signal from a galaxy far, far away, I hope I'm around to see it. So, what do you guys think? Should we invest in interstellar travel or stick to building ever larger telescopes? Is there even any point to this at all? Let me know what you guys think, and thank you for watching.